Hello and good afternoon, CTS266 Section 840 students for the Spring 2016 semester at Anne Arundel Community College. This is the CCNP Switch course, and this afternoon's video tutorial is going to be on Discovery Activity number 7 from our Cisco Learning Labs curriculum, where we're going to be taking a look at discovering and modifying spanning tree behavior. This topology should look very familiar to you. This is the exact topology that the Foundation Learning Guide highlights and uses as a guide to walk you through the different configurations for the spanning tree protocol. Now, it's very important to note that we're going to be focusing here solely in this video and this week on 802.1D, and that's a capital D there, and this is the legacy spanning tree protocol. And what we'll see when we do a show spanning trees, we're going to see the IEEE. Now, to give you a quick background on spanning tree, as you know, spanning tree exists in order to prevent loops at layer 2 because there are no TTL lifetimes at layer 2. In other words, a frame can end up circulating throughout the topology if there is a loop, and as you can see here we have a number of loops. A frame can loop throughout the topology at layer 2 and never expire. Unlike layer 3, where typically your IP packets have a TTL, or time to live, of 255. So a quick background: it was in 1985 when Radia Perlman, while working for DEC, or the Digital Equipment Corporation, and actually it's Perlman, sorry about that. All right, where she created the first version of what would become actually the spanning tree protocol. And then in 1990, what ended up happening was the IEEE published the first standard, and that was the 802.1D. And again, this is very legacy. This is big time legacy. And it's still out there. It's actually the default on the Cisco switches when we talk about the IEEE spanning tree protocol. However, in your environments today, you should be running rapid spanning tree protocol or multiple spanning tree protocol. Keeping in mind that multiple spanning tree protocol, or MST, actually uses rapid spanning tree under or behind the curtain, right? So rapid spanning tree protocol, abbreviate there. All right, and then what ended up happening was in 1998, about 8 years later, the 802.1 standard got updated, and we saw where Cisco was using PVST and PVST plus, and this is one of the things that makes the learning of spanning tree a little more difficult, a little higher degree of difficulty than some of the other Cisco concepts, is just the sheer number of acronyms and different spanning tree protocols and the way that Cisco describes it as opposed to the way the IEEE describes it. So the key thing to remember is that in 1998, the 802.1D standard was updated, 802.1D, to be called 802.1D 1998. And the key thing to note is that Cisco sort of put their little secret sauce in there, and with ISL, which is the Cisco proprietary trunking encapsulation, when you were doing spanning tree using ISL on your trunks, it was PVST, or Per VLAN Spanning Tree, meaning that there was a spanning tree instance for every single VLAN. Well, if you go back to the legacy 802.1D, and even today, the IEEE standard, so not the Cisco standard, right? Or I shouldn't say the Cisco standard, the Cisco implementation of the standard. So the IEEE standard, it was one spanning tree for all VLANs. Well, Cisco said, hold on, that doesn't make much sense, so we're going to do what we normally do, and that is we're going to take the 802.1D standard, we're going to add our secret sauce to it, and we're going to call it Per VLAN Spanning Tree. And that's when you're using ISL. If you're using 802.1q, it's referred to as PVST plus. And one way to remember this is that this is the IEEE standard protocol, and these are the Cisco, and the book refers to them as protocols, and that's fine. I like to think of them as modes. So again, Cisco took the IEEE standard, or the 802.1d98, right? They took the standard, and then they modified the standard, throwing in that the Cisco secret sauce, and they came up with Per VLAN Spanning Tree for ISL trunks, and PVST plus when you're using 802.1q. Okay? And that's where we're going to cut off right there, because again, our conversation over the next 3 weeks, and specifically this week, is all about 802.1d legacy IEEE spanning tree, and as an extension on Cisco switches, PVST, PVST plus. Well, ISL has been deprecated, its legacy, so we're going to be talking about PVST plus. And it also explains why you'll see in some of the output that we're about to embark upon here, is that you'll see alternate ports. Well, typically, an alternate port is something that you'll see with rapid spanning tree. However, it shows up in the output here of the legacy spanning tree because, again, it's PVST plus, and Cisco kind of tweaked it a little bit, and they've got the output showing just, again, additional helpful things. But in your environment, you should be using rapid spanning tree protocol, or which is Cisco's RPVST plus or PVRST plus, or multiple spanning tree, which again is just using rapid spanning tree underneath. But we will get to that in turn. So this is kind of the history again. The key thing to remember is when we see IEEE in the output, that's referring to the legacy standard, or I should say the 802.1d 1998 standard. But we're going to be doing PVST or PVST plus depending upon the trunking encapsulation that we are using. Okay, so let me go ahead and squeegee the screen here, and let's get back. And so let's go ahead and jump into the configuration component now, and we'll start out here on switch 1. So on switch 1, we'll go from user exec to privilege exec with the enable command. And actually, they're asking us to start on switch 3, so we can do that. So we'll say enable, show spanning tree. All right. Now, there's a lot going on in the output here, but let's kind of break this down. So it's per VLAN. If we had more than VLAN 1 right now, it would continue to list out the other VLANs below. However, we're talking about VLAN 1 here. Now, spanning tree enabled IEEE. They're talking about 802.1d compatible spanning tree. All right, so the root ID. Remember, one of the most important things that spanning tree does is it defines a root bridge. Now, you could just as easily say root switch. However, since this was all developed back when bridges were all the rage, the term root bridge has simply stuck. So this information right here is all about the root bridge, right? Now, you'll notice that we have this other category here called bridge ID, and you can see that the IDs of the bridge are different. Now, this is the local switch. So this would be switch 3's information. So I can see switch 3's priority. I can see the MAC address for switch 3. I can see the timers for switch 3, and I can see the MAC address table aging time for switch 3. Again, bridge ID information listed here is about the local switch. The information listed up here under root ID is for the root bridge. Now, when we talk about the root bridge, it's going to be elected based off of the bridge ID, which is made up of, and I'll draw it out over here. So the bridge ID is made up of a priority, which is in increments of 4096, and it goes from 0 to 61,440. And then the other part of that is the MAC address. Whoops, sorry about that. Is the MAC address of the switch, and then the VLAN ID. And I think I'm actually drawing this, could be drawing this backwards. So I have to take a look at that, make sure. I'm trying to do this off of memory here. And the VLAN ID. So the thing to remember again is that in choosing the root bridge, the first value that's looked at is the priority, right? Now by default, what is the default priority? By default, the default priority is 32,768 plus the system ID extension. Now the system ID extension is simply the VLAN number, right? So when we look at VLAN 1 and we see that VLAN 1 has a priority of 32,769, it's simply the default priority 32,768 plus 1, and that gives us 32,769. Now the three switches that we have that are all connected together here all have the default priority, because again, if we've just taken these switches out of the box and we've plugged everything in, then what's going to end up happening is, and yeah, I was absolutely right here. So VLAN ID is not there. So we're looking at the bridge priority, or the bridge ID, I should say, is 8 bytes. In fact, it's the priority, and then it's the MAC address is this whole thing. So we had it right at the beginning there. And so again, the priority is 2 bytes. This just dawned on me. And then this is 6 bytes. And remember, 6 bytes is 48 bits. And your MAC address is 48 bits. Okay, so we've got our bridge ID here. And then we add in the system ID extension, which is simply the VLAN number. So that's how we get to this 32,769. So all of the switches have the default value. So then, if the priority is all the same and we have a tie, we then go and look at the lowest MAC address. And so it's lowest priority, or actually I should come down here, lowest priority value would win out, or if the priorities are all default, we're going to come to the MAC addresses. So you can see AA, BB, CC, 00, those are all the same, but then it's 2 Baker and then 22, or 22 I should say, because again, these are hexadecimal characters. So 22 and 2 Baker, well, 22 is lower than 2 Baker, therefore this switch is going to win out, and it's going to be the bridge. Now, the rest of this output here, we can see we've got Ethernet 01, 02, and 03. And here is the role. Now, alternate, you will see this listed out when you are doing PVST plus. It'll say alternate. And again, the concept of the alternate port is more of the rapid spanning tree, but the reason that Cisco does this is because there's no harm putting it in the output here, because if we were to transition to rapid spanning tree, then that is what those ports would be. And we'll get into the port states and all of that in turn. And then you can see we have our root port. And real quickly, the root port is the port that is closest to this root bridge on this switch, or in other words, on switch 3. And then we have our cost values. The cost values are based off the speed of the link, and so 100 is a 10 megabit per second cost. Is a 10 megabit per second port speed. 19, as we've seen before, would be for 100 megabits per second. 4 would be for 1 gigabit per second. And 2 would be for 10 gigabits per second. And again, this is all dealing with legacy 802.1d 1998 spanning tree. Okay, so let me go ahead and clear the screen here. And let's come back and let's go ahead and in turn we're going to take a look at switch 2, because what we're trying to do right now is we're trying to discover which switch is the root bridge. So we looked on 3, and we saw that it wasn't 3. If I say show spanning tree, and we look here, is this switch the root bridge? And again, it's a very simple comparison that needs to be made. I say, here's the root bridge information. There is the MAC address for the root bridge. Remember, that's the MAC. Here is the bridge ID information for the local bridge. In other words, switch 2. Is switch 2's MAC address in there as the root bridge? It's not, and you can see it's 2 and then a 6, which is higher or greater than in bit value positions than 2, 2. So therefore, this switch that's here, it's not switch 3. We know it's not switch 2, so in other words, it's got to be switch 1, and probably why they have us going backwards here, 3 to 2 to 1. So again, let's go ahead and clear the screen and scoot back to the cursor, and let's go to switch 1, and we'll say show span. Now before I hit enter here, the nice thing is if you enter that command, show spanning tree, on the root bridge, it is going to tell you that you are on the root bridge. And again, this is critical here, for VLAN 1, because we're talking about per VLAN spanning tree, right? So there can be a different spanning tree instance for every single VLAN, and that will actually allow me to load balance by splitting the VLANs up. And we'll get to that in turn as well. But remember, we're only seeing one VLAN here. So for this VLAN, it says this bridge is the root, because if we look here, the MAC address for switch 1 is right there. So switch 1 is the bridge ID, and switch 1 is the spanning tree root bridge for VLAN 1. Now, something key to point out. We've got to identify the root bridge first. The second step, and I'm going to talk a lot about this in terms of the strategy that you should use when trying to solve spanning tree root port election, designated ports, and blocking ports, right, or non-designated ports. And so one key concept is that on the root bridge, every port for the root bridge will be a designated port, and it will be forwarding for the VLAN in question, for which it's the root bridge. And it makes sense. There's some directionality to the port role, either designated or root. So think of designated as downward facing, right? It is a downward facing port. So it faces away from the root bridge. So if I have switch 1, and let's say we're looking at it like this, and we've got switch 2 and switch 3, and they're connected like this. If this is my root bridge, I immediately know designated port, because from a layer 2 spanning tree topology perspective, those designated ports are facing downstream from the root bridge, away from the root bridge. And we'll say that these are all fast Ethernet ports here, with 19 as the cost for the links. So then, right, we determine, so again, step 1. So step 1 over here. Determine the root bridge. If the priorities are all the same, if the priority is the same, we go to MAC address, and it's always lower, and that's the key thing to remember with spanning tree. Lower is always better, and you will never end up with a tie. Now, there can be ties along the way, right? You could have the same root path cost. You could have the same upstream bridge ID, right? But ultimately, there will never be a tie, because you'll get down to a port number, right? Upstream port ID. So, and again, we're going to get to that. So the first number 1 is root bridge. We want to figure out who the root bridge is. The second step is to label the to label the root bridge designated ports. And again, it's just every port on that root bridge for which that root bridge is the root, which is for every VLAN for which that root bridge is the root. So we label the designated ports. Now, the next thing that we do is we're going to say, what are the root ports on the non-root bridges? Well, 2 and 3 are not the root bridge. Switch 1 is. So the root port is the port that is closest, and by closest I mean has the lowest cost to get to this root bridge. So when we look at switch 3 here, right, it's got that outgoing interface and that outgoing interface. If switch 3 goes this way to get to switch 1, it's going to incur a cost of 19 on that outgoing interface, and then another cost of 19 on that outgoing interface. So going this way, the root path cost is 38. And going this way, the cost is 19. So there is my root port. It's that simple. Now, switch 2, it's the same thing. Switch 2 to go this way, the cost is going to be 38 because he's going to incur a cost of 19 on the outgoing interface there and 19 on the outgoing interface there. If he goes this way, the cost is 19. So, boom, root port. So now we're left with this segment here, right? So the question becomes, for every segment, the question's going to become, first of all, who is sending the BPDU, or the Bridge Protocol Data Unit, right? And that's how Spanning Tree communicates throughout the layer 2 domain, is with Bridge Protocol Data Units, is which switch, is it going to be 3 or 2, that is sending the BPDU with the lowest root path cost? Well, switch 3 is going to say, I can get there in 19. Switch 2 is going to say, well, hey, wait a minute, I can get there in 19. So the lowest root path cost is going to be a tie because they're both 19. So then we have to move down to who is the lowest sender MAC address, right? And so what that comes down to is switch 3 has a MAC address and switch 2 has a MAC address. So whichever one of these guys has the lower MAC address, and let's say that they're all the same to the last hex character, and his last hex character is 2 and his is 3, which means that switch 2 says, hey, I've got the lowest bridge ID between 2 and 3. I've got the lower bridge ID on this segment, therefore I will determine that I'm the designated port. And that's when switch 3 says, you know what, we need to prevent the loop. And it goes into the blocking state on that port. So if we redraw this without the link that's blocked, this is the topology that we end up with switch 3, switch 2, and switch 1. There's our topology. And I always encourage students, after you work something out by hand with Spanning Tree, to go ahead and redraw it and leave out the block links to see, do I have a loop? Well, clearly there's no loop here because, again, that link that was right here, and this is not doing too good at the dotted lines, that link is blocked, so it's not part of the setup. Okay. So let's squeegee the screen off. So now we know the root bridge. The root bridge is switch 1. And now what we're going to do is we're going to take a look at, all right, so we've got all 3 switches here. The MAC addresses. So the port roles. So we took a look at the different port roles, right? And remember, on the root bridge, every port for the VLAN, right, will be a designated port for the VLAN for which it is the root bridge. Those will be designated ports. If I go over to switch 3, you can see that we've got alternate ports, and we also have, let me change the color here real quick, we also have a root port, again, because that root port is the closest port, and when we say closest, we mean the lowest cost to the root bridge. So Ethernet 03 has the lowest cost to the root bridge. And if I come over to the main diagram here, once you know the root bridge, that's where it becomes critical. So this is the root bridge. So once I know this, what do we know about these two ports? Exactly. They're both going to be designated ports. So then we're dealing with all 10 megabit per second links, so the cost is 100 for everything. So these links all have the same, segments all have the same cost. So then for switch 3 to get to the root bridge, it's going to cost him going this way 100. Going this way, it would cost him, again, outgoing ports, 100, 200 going that way. So where is his root port going to be? Exactly. His root port will be that guy right there, Ethernet 03. On switch 2, very simple. It's 100 to go that way, right? So the cost for me to go that way from switch 2 is 100. From switch 2 to go that way, the cost is 200. So this is the root port. Now, that brings us to this segment right here. And we have, these two segments, I should say, these two network segments. So each of these links, this is not an Ether channel, is its own individual segment. So we're going to have to do the same thing for both. So this is where we say, okay, well, what's the lowest root path cost? That is my first tiebreaker between switch 3 and switch 2. So switch 2 is going to be saying, hey, my root path cost is 100. And switch 3 is going to say, yep, so is mine. So then what it comes down to is the lowest sender's bridge ID, or in other words, the lowest sender's MAC address. So who has the lower MAC address here? Is it switch 2 or switch 3? And let me scroll back up here. I can't remember what the MAC addresses were for either of those. So switch 3 ended in, actually that's totally different. So let's do this here real quick. I'll leave that on there. So switch 3 was 2 Baker 00 and switch 2 was 2 6. Well, 6 with the bit positions is less than Baker, therefore switch 3 is sending a higher higher MAC address when compared to switch 2. So therefore switch 2 will say, I am the designated port for that segment, and when we go to evaluate this next segment, it's the same thing, because on this segment here, between switch 2 and switch 3, they're both sending the same BPDUs, therefore switch 2 says, yep, and since I've got the lower MAC address, I will be the designated port on this segment as well. So what that means is blocking and blocking. And if we redraw this without the blocking links, what we get, switch 1, switch 2, and switch 3, we get this. And there we go. And there's no loop here because, again, these two links that are here, that you see here, that would be there, they're blocking. And so that prevents the loop. And that's really how Spanning Tree walks through with the BPDUs, with each switch sending BPDUs to announce its values. Excuse me. Okay. So now let's go ahead, and it looks like we're going to be making a change here. And again, when you see that alternate, right, I prefer the term non-designated because we've got designated ports, and then I like to call them non-designated ports. But PVST Plus, right, Cisco's Per VLAN Spanning Tree Plus, remember they took the IEEE 802.1d standard and they added their Cisco secret sauce to it, and it's a IEEE 802.1d compatible version of Spanning Tree, but Cisco calls it PVST when you're using ISL for your trunk links, or PVST plus when it's part of that 802.1 queue. All right. So we've got those. So now we're going to talk about changing the spanning tree priority. So we saw on all of the switches what the priority was. The priority by default is 32.768 plus the system ID extension. So keep in mind that we can change the priority in increments of 4096 by starting from 0 and going up to 4096. So we're going to make switch 2, it looks like, the root bridge. So how do we do that? Well, we go into global config and we say spanning tree VLAN 1, spanning tree VLAN 1 root primary. Now, this is going to give us an interesting result here, because what I've just done is I ran a macro. And remember, a macro is kind of like a little script that runs a certain series of commands in the background. So we say root primary, but what it's actually doing when I say do show spanning tree is it's actually running a command in the background to set the priority to 2, 4, 5, 7, 6. And I'm having some problems highlighting that there. So you can see now for VLAN 1, it says this bridge is the root. So switch 2 is now the root bridge. There's my MAC address for switch 2. The MAC address is here. And why is it the root bridge? Well, because we've just lowered the priority to 2, 4, 5, 7, 6. And you're probably saying to yourself, well, wait a minute, Travis, it says 2, 4, 5, 7, 7. Exactly, because then we add in the system ID extension, which is the VLAN number that we're discussing, and that is where we get the priority, 2, 4, 5, 7, 7, right? But again, that is the value that is divisible by 4096. And so you'll remember I commented that this right here, spanning tree VLAN 1 root primary, that this is a macro, M-A-R-C-O, because in the background, it's actually checking to see what the other bridge priorities are, and it's going to lower the bridge priority to 2 steps below the lowest bridge priority. So if the lowest bridge priority is 32.768, if I were to subtract 4096 from this, we would get 2, and then I'm going to test my math skills here, 7, 6, 2. That can't be right. Sorry, I got this backwards. Not 2, it'd be 12, 8, so 28. Sorry about that. So 28, 6, 7, 2. But you can see we went down to 24, 5, 7, 6. So if I take 4096 away again, we should end up with 24, 5, 7, 6, right? And we do. So that macro basically drops the root bridge priority for the VLAN in question by 2 increments of 4, or 8192, right? It drops it by 8192. And it puts it down at 24.576. And again, this is assuming that all of these switches have the default bridge priority value. So if I squeegee off here and we take a look, if I were to say do show span, and actually you can see it there at the bottom, this is the root bridge for VLAN 1. What is the role of every port in VLAN 1? Exactly, designated. So let's do this. Let's come back over to the main diagram here, and now let's work this out. So switch 2 is now the root bridge. And so what that means is Ethernet 03 is a designated port, just like we saw. 01 is a designated port, and 02 is a designated port. So now the question becomes, for switch 1, which port is my root port? Well, obviously it's going to be this one here because it's directly connected to the root bridge, so this would be the root port. And remember that every switch can only have one root port. Only one. Now we get down to switch 3. We know it's not going to go that way, right? So we know that that is not going to be the root port. It's going to be one of these two ports that are directly connected to the root bridge. So now we go into we look at our strategy and we look at the order of operations. So the first order of operations is which of these two links has the lowest root path cost. In other words, between these two links, who has a lower cost to get to the root bridge? Exactly. These are both 10 megabits per second. Therefore, their costs are going to be a tie. The cost will be 100. So now we go to the second tiebreaker. The lowest MAC address, or the lowest bridge ID, the lowest MAC address, well, guess what? The MAC address that's being sent from the root bridge is the same for both of these. Right? So both links, switch 3 is going to see for the root port, he's going to see the same MAC address coming in because he's directly connected to the root bridge. So then again, it's a push. We have a tie because the MAC address that's coming out here for the root port election from the root bridge is the same. It's the same switch, even though we've got these multiple segments. So then we get down to the final tiebreaker. And the final tiebreaker is the port number. And this is where it becomes critical, and it's all about perspective, because you'll hear it mentioned two different ways. So the first way you'll hear it mentioned is the lowest sender port number. So from that perspective, here's the root bridge. Which of these two port IDs from the sender, right, are lower? Well, it's Ethernet 0, 1. So in other words, this port would be a forwarding port, and this port would be the blocking port. The other way you'll hear it referred to, sender port ID. So we'll say sender port ID, and then you'll hear it referred to as upstream port ID. And it means the same thing. I always like to think of it as the sender. If I'm talking about the sender port ID, it's from the perspective of here's my sender, and he's sending it this way. When you say upstream port ID, it's viewed from the perspective of this switch here, because who is upstream toward the root bridge? And so then again, it would be that this guy right here, because he's receiving port ID of 3, he will be blocking. So now we're left with that segment right there. So again, on this segment, because each switch already has its root port, right? There's the one root port for those switches. Here's the blocking one there. So now on this segment, who's going to be the designated port on this segment? And the designated port is responsible for sending along the BPDUs from the root bridge. So who's going to do that? Is it going to be switch 3? Or is it going to be switch 1? Well, the lowest root path cost. Exactly. It's a tie, right? Because switch 1 says it's 100. Switch 3 says, yep, I can get there to the root bridge over here in 100 as well. So we've got a tie. Then it goes to the lowest MAC address. Well, who has the lower MAC address? Well, we've already saw that switch 1, when everything was the default for the bridge priorities, that switch 1 is the root bridge. So we know he's got the lower MAC. Therefore, that is my blocking port. And this, on that segment, would be the designated port. And again, if we added another link in here, it would be the same thing. Blocking and designated. Remember, for every segment, right, one of those ports would be in a forwarding state. Okay? So if I redrew this topology without the blocking links, and for root bridge, switch 1, switch 2, and switch 3, what would we have? We would have that link right there. We would have the one designated port to root port link, and then these guys are blocking. So that's what the topology looks like when we have switch 2 as the root bridge. And every time we move the root bridge, spanning tree needs to recalculate, right, what the port roles will be. Who will be the designated port? Who will be the alternate ports, or I should say the non-designated ports, which are the blocking ports? Who's going to be the root port? And this is where it becomes critical that you never want to allow spanning tree to make the determination on its own. So if this was a distribution layer switch, say distribution layer switch 1 and distribution layer switch 2, and this was our access layer switch, you definitely want one of these two switches to be the root bridge for VLAN 1, or for whichever VLANs you're using, and then the other to be the secondary root bridge, because you want to make sure that, let's say that switch explodes, right, that you have a deterministic failure. And what I mean by deterministic failure is that when that switch blows up, you know exactly how things are going to reconverge, which means this switch over here becomes the primary root bridge, and now we start forwarding this way instead of maybe forwarding that way, right? So typically your distribution layer switches are going to be your spanning tree root bridge, the primary root bridge and the secondary root bridge. And when we get into the first hop redundancy protocols, we'll talk about how you want to split the load up. So maybe VLAN 1, 3, and 5 over here are going to be, this would be the root bridge primary for 1, 3, and 5, and this would be for 2, 4, and 6. And if that's the case, you want to make sure that the first hop redundancy protocol, GLBP, HSRP, or VRRP, is doing the same thing, where their primary, right, if we said VRRP or HSRP, where the primary for the VLAN in question is also, this is also the spanning tree root bridge for those same VLANs, right? Okay, so let's continue on here, because now we're going to start to manipulate things, and we're going to talk about the port priority. So we're going to change the cost of an interface, and so in order to manipulate things, talking about path manipulation, and a quick note, remember that the root bridge isn't telling the other switches how to forward their traffic, right? So this is very different than layer 3 traffic engineering. So the whole concept of spanning tree is the root bridge is the central point in the spanning tree topology, and then all of the other switches make their determination independently as to how they're going to get to the root bridge. So it's not that the root bridge is saying, oh, you have to forward your traffic this way. The root bridge is simply the point of reference for the layer 2 spanning tree topology, or the layer 2 domain. Okay. All right, so now we're going to talk about path manipulation. And there's two ways that we can do the path manipulation. We can manipulate the cost. We can manipulate the port ID, right? And so it looks like we're going to do, let's see what we're doing here. They've got us, the port ID consists of the port priority and the port number. So they want us on switch 3. And remember, on switch 3, what are we looking at right now? Well, on switch 3, this is our root bridge with the way everything stands. So we know that the root port is here and that this guy is blocking, right? So on Ethernet 01, who is the root port of switch 3, because of the lower port priority, Ethernet 02 has a port priority of 128.3, and we'll jump in there and take a look at that. Let's see here. What do we have? So they basically want us to change the cost of Ethernet 02. And this must be, yeah, so we're going to change the cost of Ethernet 02. So let's clear the screen here. Let's jump into switch 3. And if we were to say show spanning tree right now, you can see that Ethernet 02 and 03 are both blocking, right? So 03 was on this side. He lost out between switch 1 and switch 3, and 02. So the forwarding port, the root port for switch 3 is Ethernet 01. And so what we're going to do now is we're going to change the cost of Ethernet 02, and here's the costs are all 100. We're going to change 02 to have a cost of 16 as opposed to 100. Because remember, before we got to the port number and before we got to the MAC address, the lowest MAC address for the root bridge, what was the type? What was the criteria? The criteria was lowest root path cost, or closest root, closest port to the root bridge, which meant the lowest cost. But they tied because both of those links were 100. So now what we're going to do is we're going to manipulate that. We're going to go into interface Ethernet 02, and we're going to say spanning tree VLAN 1, and we're going to lower the cost. I can actually, we'll just set it, it says 16, but we'll dump it down to 19 here. Now, remember what we had up here, right? Ethernet 01 was the root port, and then we had 2 blocking ports. Now let's take a look and see what we see. So now Ethernet 01 is no longer the root port, it's the alternate, or the state is a blocking port, right? The root port is now Ethernet 02, and the state is listening. So it's transitioning from the blocking state to the listening state. It'll be in the listening state for 15 seconds, and then we missed it. And then it goes into the learning state for 15 seconds, and that's where this forward delay timer comes in. So we're being delayed in both the listening and the learning states before we get to forwarding. And so now what do we have? We have the port with the lower port cost is now the root bridge. So if I were to go into interface Ethernet 01 and say spanning tree VLAN 1 cost and say 18, what is that going to do? What port would be the root port now? Exactly, Ethernet 01. So do show span, and so we'll keep up with it here. So it's in the listening, and it'll stay in the listening state for 15 seconds. And there's your learning state. And we'll take a look at some debugs here. I should actually be debugging spanning tree events. But again, it's all about who's got the lowest root path cost. And that port will be the root port, and we should be in the forwarding state, and now we are. So if I went back into Ethernet 02 and I said, no, I want Ethernet 02 to be the root port here, I would say spanning tree VLAN 1 cost, and what would I have to put in there? Something lower than what? Lower than 18. Exactly. Because if I put 18 in there, does anything change? Why is nothing going to change? Exactly. Because if it's a tie there, we go to the MAC address. The root bridge is the same MAC, right? So that we have another tie. So then we go to the lowest upstream port ID, which will be Ethernet 01. So I would have to say something lower than 18 to make that port, and again, we're going to have a 30-second delay here, to make that port the root port and for it to be in the forwarding state. So again, that's how you would manipulate the root port based off the cost. And I love how they had us they set it up here so that we got onto switch 3, which has 2 links, both connected to the root bridge. And so again, as soon as we made that change, then we ended up with a new root port. All right, so now we're on, if you're following along in the lab, I'm on step number 8 here. And in step number 8, we're actually going to kick on the debug spanning tree events on switch 3. So let's say debug spanning tree events. And this is going to give us some additional information. So now we're going to go into interface Ethernet 02. Oops, sorry. First we're going to get into global config. Interface Ethernet 02. And now they want us to shut this down. Let me make sure. Changing the cost of 02 on switch 3. So port 1 should be blocking here. And it is. Okay, so you're going to see what happens here with this sort of this quote-unquote this alternate role that we have for Ethernet 0.1. So what I'm going to do now is I'm going to shut down Ethernet 0.2, and that is currently our root port because it has a lower spanning tree or lower root path cost. The cost is 17. All right, so let's squeegee the screen off here, and let's say shut, and we're going to see some debug information come to the screen. You can see that VLAN 1 new root port is now Ethernet 0.1, and it's transitioned into the listening state, right? So if I were to say do show span, you can see we're actually 15 seconds. We're already in the learning, and that's what that debug is for there. Shows that we transition to the learning, and then 15 seconds from now, we're going to transition into the forwarding state for Ethernet 0.1. And there we go. And you'll notice that we have a topology change notice. Now, this is one of the keys when we start to talk about the tools in the spanning tree toolkit. We're going to be talking about Portfast or spanning tree Portfast with legacy 802.1d spanning tree. And what Portfast allows us to do is it allows us to skip the listening and the learning states and transition immediately to the forwarding state. Because you'll notice we've been sitting here, we have to wait 30 seconds for this to reconverge before it shows that the ports are in a forwarding state, right? Now, when we do Portfast for a host or a server-facing port, we'll turn on spanning tree Portfast and we'll skip those times. All right, so now we're going to talk a little bit about the timers, the hello time, the forward delay time, and the max age time. And so let me get the pen here. Now you can see there's two sets of times. And the key thing to remember is with 802.1d spanning tree, when you see the local settings, these will be the settings that are defined locally. These are the settings defined on the root bridge. But the key is, if you manipulate these timers, right, there's a BPDU being sent every 2 seconds. When we talk about the max age time, that's the amount of time or the maximum amount of time that'll pass before the bridge port, right, or the designated port is going to save the BPDU information that it's receiving. I should say the root port is going to save the BPDU information that it's receiving before it ages out. So think of this as almost like the dead timer, right, with OSPF, where it counts down from 40 seconds, and when it gets down to 0, the adjacency is gone. And it's the same thing with the max age time. The port that is receiving BPDUs, right, the root port that is receiving BPDUs, is going to cache those BPDUs in memory for max age time. Now, it should be getting a BPDU every 2 seconds coming from a designated port. Because remember, the designated ports are downstream facing, and those are the ports that are sending the BPDUs along. The max age timer, we would have to miss 10 BPDUs, which would equal 20 seconds, and then the port will immediately, or I should say the switch is immediately going to think that it could possibly be the root bridge on for that port, and it'll start sending BPDUs out declaring that fact, and we'll talk about that a little bit as well as we move on here. And then the forward delay. Now remember, this applies to both listening and learning. So it applies to both the listening and the learning states. And that delay timer right there, that 15 seconds, it's 15 seconds for listening and 15 seconds for learning for a total of 30 seconds. And this was one of the reasons that Rapid Spanning Tree, when it came out, was so popular, because you can cut that down to about 6 seconds because you no longer go through the listening and the learning states. Okay. So now what we're going to do is we are going to unblock, or I should say no shut, Ethernet 02. So interface Ethernet 02, we're going to say no shut, do show span. We should see some debug information here. And there we go. So you can see that it's going into listening. Ethernet 01 went into the blocking state immediately. And now Ethernet 02, because it has a lower cost, is going to be our root port, and it's going to transition through the listening. You can see that now we're in the learning, and then another 15 seconds. And so now that we've transitioned back, let's see if it has us do anything. So it's not in here, but let's spice this up a bit. We talked about tweaking the port cost. This is sort of a less popular thing that gets done. Remember, it's the upstream port ID, right? So right now on switch 3, if I say do show span, the root port, let's make these the same. So we're going to say spanning tree VLAN 1 cost 18. So we'll make those the same. So the spanning tree cost is going to be the same, which means that Ethernet 02 would be blocking because, all things being equal, the lower upstream port ID is going to be on Ethernet 01 up on switch 2. So let's let this settle down here. We'll let it go into the forwarding state here. We should see a message. And we're going to go to switch 2, and we're going to tweak the port ID. And by default, you can see right here, the priority is 128. And then you've got the port number. Now, lower is always better. And so I'll drop it down on the upstream switch 2. And let's confirm here, switch 2's Ethernet 03 plugs into the Ethernet 02 here. So all we would need to do is lower the priority on Ethernet 03 so that it's lower than Ethernet 01. And then this segment should be forwarding, right? And the root port would be Ethernet 02. So we did the cost from switch 3's perspective. Now let's take a quick look at the port priority and the port ID on switch number 2. So let's go into, what do we say, interface Ethernet 03, and I'm going to say spanning tree VLAN 1, and there's my port priority, right? So now actually the increments, that's right, increments of 64, and it goes from 0 to 192. So 128 is my default. Well, if it's got to be in increments of 64, let me drop it to 64. And let's go back to switch 3 where we've got some debugs and take a look at what's happening right now. Ethernet 01 no longer sees a lower upstream port ID on Ethernet 01 on switch 3 because it's changed. We changed it so that the lower upstream port ID, do show span, is now coming, or is seen from switch 3 on Ethernet 02, right? And the tough part about this is you can see that these values are the same, and the priorities here, these are for the local ports. So it doesn't really tell you, oh yeah, it's because the port priority upstream has changed. You would have to go to switch 2 and say do show span and take a look at that. So this is now the lower sender port ID. And we can do it in increments of 64. If I go into interface Ethernet 02, and let me confirm that that faces 01 down here. No, actually it's 01 to 01. So we want to go into, glad we looked at that. Interface Ethernet 01, and I said spanning tree VLAN 1, port priority 0, do show span. Take a look at that. Now it's 0, 128, and 64. So now this guy, Ethernet 01, should be, and there we go. Look at that. We've got Ethernet 02's transition into the blocking state, do show span. So who is my root port again? It's Ethernet 01, because again, the port priority as a tiebreaker after lowest root cost path, the lowest MAC address, and then we get down to the port ID, right? The lowest sender port ID is the priority and the port number, And that priority value has been lowered on the other side here. So that's why we're back now with Ethernet 01 being the root port. All right, so to wrap this activity up, what they've got us doing is now we're going to go ahead and we are going to transition to rapid spanning tree. And this is a good place to stop because, again, we're not covering rapid spanning tree this week, but let's go ahead and say spanning tree mode. I'll do a question mark. You can see there's only 3 modes we can choose from. It's MST, which is multiple spanning tree, PVST, which is per VLAN spanning tree, and rapid PVST. So we want to say, and actually before we do that, let me say do show spanning tree summary, because this is important. I say do show spanning tree summary, and you can see right here, switch is in PVST mode. Right? Now watch what happens when I say spanning tree mode, mode rapid PVST. When I say do show spanning tree, and there go the proposals, right? And that proposal process that you see taking place right there, that is what is going to shorten our forwarding time, so we're not sitting around for 30 to 50 seconds. Do show spanning tree summary. The proposals will be key. Now look at the mode it states that we're in. Switch is in rapid PVST mode because we changed from the IEEE 802.1d. We are now running the rapid spanning tree protocol, but remember, it's Cisco's secret sauce that they like to call RPVST, right? And that would be the ISL or RPVST plus with 802.1q. And so if I were to say do show span, you can see that we've got the changes that have been made. Now take a look here. We'll talk about this more later. When you see the peer STP, what that means is the peer to switch 3, we're on switch 3, these peers out these links over here are running legacy 802.1d spanning tree. So if I come over here to switch 2 and I say do show span, you can see that he doesn't say peer STP. Again, he's not running rapid per VLAN spanning tree yet because he still says IEEE there, and do show spanning tree summary shows switch is still in PVST mode. Now, are these interoperable? Absolutely, 100% interoperable. But we're going to go ahead and say spanning tree mode rapid PVST. Now, we're not debugging here, but if I go back over to switch 3 and I say do show span again, my link or links to that switch no longer show peer STP because switch 2 is now running rapid spanning tree protocol. So let's do the same thing here. So spanning tree mode rapid PVST. If I go back to switch 3, all of the links now no longer show peer STP because we've changed the spanning tree mode on all of the different switches. So now let's take a look at the proposal process and what that buys us, right? So the convergence time of rapid spanning tree protocol is exponentially quicker than the legacy 802.1d spanning tree because of the proposal process. So on switch 3, if I said, and we have it up there already, do show span, you can see we've got this alternate port which is blocking. Well, rapid spanning tree protocol has already pre-calculated the paths. So on switch 3, if I were to go into interface Ethernet 02 and I were to say shutdown, let's see just how quickly do show span it converges. And take a look at that. No listening, no learning, right? I mean, it was less than a second. It was almost instantaneous. If I come back up here to switch 2, right, you can see that the links are forwarding because he's the root bridge, but that happened rather quickly. Now, what happens if I say no shut? If I try to bring it back up, do show span. And you see how quickly it did that. There's no listening, no learning. We went literally from disabled to, and I think we're to blocking, right? I think we're doing Ethernet 02 here. So again, if I say shut on Ethernet 02, watch how quickly, look, it's already in the forwarding state. So less than a second to converge from a spanning tree perspective. Now, compare that with a 30 to 50 second outage that could possibly take place while we're waiting for the forwarding delay in the listening state. And then we've got a 15-second forwarding delay in the learning state. And then we finally transition to forwarding. So again, this is really one of the key reasons to be running the Rapid Spanning Tree protocol. All right. Well, that is going to do it for Discovery Activity 7, which is discovering or exploring the legacy 802.1d spanning tree, or just discovering spanning tree in general and modifying the behavior. And we took a look at how to do that layer 2 traffic engineering, where we can manipulate the spanning tree port cost and drop it to a lower value to make it look more attractive. Or you could look at the upstream port ID and manipulate the priority values, right? By default 128 in increments of 64. Okay, well, that wraps up this video, this discovery activity, and I will see you guys on Monday.